All right, good afternoon, well, good morning or good evening for those of you all over the world. It is a great pleasure and honor to welcome Professor David Simchi-Levi to our seminar series in the Mechanical and Industrial Engineering Department at UMass Amherst. David is a professor of engineering systems at MIT and leads the data science lab there. David's contributions to advancing both the science and practice of supply chain management, business analytics, and data-driven decision-making are deep and wide. He has a true gift for identifying high-impact problems and finding innovative and practical but theory-driven solutions. As a result, his work has been widely recognized. He's an Informs Fellow and Emson Distinguished Fellow. He has received the 2020 Informs Impact Prize for his innovative work on the identification and mitigation of risks in global supply chains, the 2020 Informs Koopman Award for Outstanding Publication in Military Operations Research, Ford Motor Company's 2015 Engineering Excellence Award, the 2014 Informs Wagner Prize for Excellence in Operations Research Practice, 2014 Informs Revenue Management and Pricing Section Practice Award, the 2009 Informs Revenue Management and Pricing Section Prize, plus a multitude of other awards and best paper awards garnered over time. David is currently Editor-in-Chief of Management Science and was previously Editor-in-Chief of Operations Research and Naval Research Logistics. The first two, Management Science and Operations Research, as most of you know, are the flagship journals of the Institute of Operations Research and Management Sciences. He has driven lots of important initiatives in these three publications and advanced their long-term mission and impact. He has also made an indelible mark in practice, especially through direct technology transfer in the three companies he has founded or co-founded. Logic Tools in 1995, providing supply chain optimization software solutions and professional services. Logic Tools then became part of IBM in 2009. Operations Rules, Ops Rules, in 2012. It's an operations consulting company, and it became part of Accenture in 2016. And then finally, Opalytics in 2015. It's a cloud analytics platform focusing on operations and supply chain decisions. And this then became part of Accenture Applied Intelligence in 2018. Now, last but not least, greatest accomplishment, David was my PhD advisor. We won't say how many years ago. I am forever indebted for that time and the many opportunities that have followed since. He definitely changed the course of my life, as I'm sure he has done so for dozens of PhD students that have been lucky to work under his supervision throughout the years. Thank you, David. The floor is yours. Please share your screen.
Thank you so much, Anna. It's really a pleasure to be here. And thank you for organizing and opening this to members of our community beyond a single university. That's great. Let me share my screen here. Share, I think you can see it. Let me click here. Hide the bar. You can see my screen, right?
Yes. Go ahead.
Beautiful. All right. So welcome, everybody. It's, as I mentioned, pleasure to be here. I'm going to talk about statistical learning in operation, specifically the interplay between online and offline learning. It's appropriate to start this talk by describing the environment at MIT that led to this research. At MIT, I lead the data science lab. The data science lab is a partnership between MIT and about 20 companies, focusing on some of the most challenging problems that these companies have by bringing together data, models, and analysis. And going all the way from the analysis to implementation, as you will see in a second. We have partners in a variety of industries, from oil and gas, retail, government, insurance, airline, industrial equipment, manufacturing companies, software companies, and we have global footprint. Let me give you a few examples of the type of work that we do at the data science lab, some of which specifically led to the research that I will report here. An area of research that is very active in the lab is supply chain resiliency. We started looking at supply chain resiliency way before the pandemic. Now it's a very hot topic. We started looking at that in 2012 after events like the tsunami in Japan and the flood in Thailand that year, as well as the 2010 volcano eruption in Iceland. We were fortunate enough to collaborate with the Ford Motor Company and develop a new way for companies to quantify the level of resiliency of their supply chain, identify hidden risks, and develop mitigation strategies. And I was fortunate enough also that Ford allowed us to publish a paper with a detail about the technology and the impact on the Ford Motor Company. This paper was published in 2014. Between 2014, when we published the paper, and the beginning of the pandemic, I was knocking on many doors, trying to convince companies that in addition to focusing on cutting costs and supply chain efficiency, they should also focus on resiliency, very little interest. Perhaps we had about 10 companies that joined us and implemented our models, our concept, our technology. Everything changed at the beginning of the pandemic, but perhaps not in the way you expect. Think about January 2020. The pandemic is in China. It's not in North America. It's certainly not in Europe. I started collecting data in January on what's happening in China, and I realized that I can use a technology that I developed 6 years earlier to understand the impact of what's happening in China on global supply chain. And I very quickly, beginning of February, submitted a paper to Harvard Business Review that said that COVID, what's happening in China, will stop supply chain in North America and in Europe. And I was very specific, not only stop, by mid-March. And this is exactly what happened. If you look at the bottom of this slide, I'm quoting a couple of articles, one in Fortune on March 17 and one in the New York Times on March 18, one emphasizing supply chain is stopping in Europe, and the other one, supply chain is stopping in North America, precisely consistent with our prediction. And then 2 months later, in April of 2020, I published a follow-up that highlighted the need for supply chain stress tests in critical areas, and I enumerated them: healthcare, life science, semiconductor industry, areas that are critical to the national security of the country. I was pleased to see that in the US President economic report that was released in April of this year, there was a section focusing on the type of technology, the type of performance measures that came out of this research, in fact, directly citing the work that was done at the MIT Data Science Lab. In parallel, in 2020, Accenture signed a big contract with MIT to scale up our technology and to bring it to a variety of industries. In fact, there is a YouTube that was just released yesterday where Accenture describes the impact of this technology and the lessons that they learn together with their client about the resiliency of supply chain. So that's certainly one area. A second area of work is around price optimization. For online retailers like Groupon, a company many of you know very well, as well as Zalando. Zalando, if you're from Europe, Zalando is the largest online fashion retailer in Europe. Our technology price product day in and day out for 1.5 million different SKUs. We also do the same thing for brick and mortar retailer like Coppel, which is a large retailer in Mexico. Personalized offering. To illustrate the research in this area, which will lead us later on to the detail of the research that I will describe, if you fly today from London to Paris, when you purchase your airline ticket, we are not involved, but once you purchase your airline ticket, our system kicks in. Think about what I'm describing. The MIT system kicks in and offer you all sorts of ancillary products, priority boarding, car rental, hotel, and the offers that you will get, the offers that Anna will get, may be different than the offers that I will get or my wife will get, because the system is learning on the fly about consumer preference and providing personalized offering to individual. The same technology was also implemented in a variety of insurance companies. Work in the area of supply chain, in inventory, transportation, procurement, for software companies like Blue Yonder, specifically on improving last mile delivery for their customers. Home Depot, focusing on trade-off between speed to increase the probability of fair purchase when customers go online, and inventory positioning. The idea is that for many products, if I can reduce the time from order to delivery, the probability of purchase goes up. But in order to reduce the time, you need to position inventory close to market demand. This increases cost. How do you balance this trade-off? Work on online resource allocation with companies like IBM, work that's still going on, and works that we did for Alibaba until about 2019. And finally, a lot of work on supply chain digitization. Throughout this work in a variety of areas, we started, my team at the Data Science Lab started getting deeper and deeper into statistical learning. And if you look at the area of statistical learning, there are two major research directions: online learning and offline learning. Let me describe each one of them. In online learning, the assumption is that no data is available at the beginning of the process. Data is generated on the fly according to some unknown model, and then decisions are made. More specifically, think about you logging in on the Amazon platform. When a customer logs into the platform observes the characteristic of the customer, what we call the feature vector of the customer, or the context of the customer, XT. Based on this, the platform make a decision, for example, recommend a specific product to the customer, or in healthcare, when you log to a healthcare platform, maybe recommend a treatment, a personalized treatment. Once we made a decision, the platform observe reward. For example, in the case of Amazon, the reward is whether the customer purchased or did not purchase the product. In healthcare, this is the efficacy of the treatment. We assume that this reward is generated by some unknown model, F star. This F star, the reward, depends, of course, on the context, on the feature vector of the customer, as well as the decision made. We will call F star the ground truth. This F star is unknown to the decision maker. And our objective is to design algorithms to maximize accumulated reward. Or equivalently, we want to minimize regret. What is regret? Regret is the difference between the accumulated reward achieved by a decision maker who knows F star, and the accumulated reward achieved by our algorithm that does not know F star and needs to learn on the fly. Offline learning is different. In offline learning, we assume that all the data is available at the beginning, and it is assumed typically that it's IID data. The decision maker cannot generate new data and then update his or her decisions. And so the idea is I have a set of n data samples. Each data point is a triplet: the context vector, the feature vector, the decisions that you made, and the reward. And the assumption is that this training data set is IID. Our objective in the offline is to design offline algorithm that will generate a predictive function f hat such that f hat closely approximates the ground truth f star. Or more precisely, we want to design algorithms such that with limited amount of data, the algorithm will generate a predictive function f hat such that with high probability, this predictive function f hat will have low error compared to the ground truth f star. The only thing that is not well defined in this definition is error. Typically, we measure error by looking at the average square difference between the estimated value and the actual value, what is called MSE, or mean square error. Our results, the ones that I will describe, hold for even more general estimation error, but I will focus here on MSE. The beautiful thing about offline learning is that in the last 10, 15 years, very powerful algorithms have been developed for offline learning that you can use in general. This is not the case for online learning. As a result, our research focuses on two important questions. The first one is it possible to reduce online learning to offline learning? Because if I can do that, then I can use all the tools that are available for offline to solve the online. We answer that question in a positive way, in the affirmative, in a paper that was just published in Math of OR. This is done with one of my PhD students, Yinjun Xu. We call this paper Bypassing the Monster. I will explain later on in the talk who is the monster and why we can bypass the monster. So that's one area of research on the interplay between online and offline. The second comes from the interactions that we had with many of the executives that use our online algorithm. Many of them said, the online algorithms are powerful, but why are you ignoring all the offline data? We have a lot of data that we collected before you implemented the online algorithm, but you are not using it. So the question that we ask in the second line of research, under what condition offline data allow us to improve the online learning, and by how much? This is answered in a couple of papers, one of which just appeared 2 years ago in ICML, and this year the longer version is published in Management Science. Today, I will mostly focus on the first question. Is it possible to reduce online learning to offline learning, use the available set of tools that exist for offline to solve the online learning problem? So here is an outline. I will start with motivation and the detail of the research questions that we are focusing on. I will explain why this is a challenging problem and pinpoint our contribution, describe in a very intuitive way a simple algorithm that we are using to reduce online to offline, and then show you the key theory and computational experiment. And this will be the beauty of this work. This work is purely theoretical, but the computational experiment shows that the algorithm coming out of the theory is extremely powerful. And that's basically the key part of the talk. And depending on time, I may describe the second line of research that I mentioned. So let's start with motivation and the key research question. And a good first step is to precisely define the contextual banded problem. Here is a definition. We are playing capital T rounds. At time little t, a customer arrives. We observe the context, the feature vector of the customer. Based on the feature vector of the customer, we make a decision. For example, a customer arrives to the Amazon platform. We observe the characteristic of the customer, and then we decide what product to offer the customer, or at what price in a dynamic pricing environment to sell a specific product. We assume for now that this decision is out of k possible decisions. So there is a discrete choice of decisions that we can choose from. I will refer later on to extensions where there are infinitely many number of decisions to choose from. The reward that we observe, right, R, has a characteristic that expected value condition on the feature and condition on the decision is the ground truth. The only assumption I will make is that the ground truth F star belongs to some general function class F. Does this make sense? General function class F, you may decide which it is. Linear, fine. Non-linear parametric, also fine. You will see examples as we go on of a variety of classes. And our objective is to design algorithms that will minimize regret the way I defined it earlier. As I pointed out a second ago, a class of function big F can be anything. Linear, high dimensional linear, maybe non-parametric, regression tree, neural network, and so forth and so on. And we want a general algorithm that works independent of the class of function F. Now, why this problem is important? Because this is one of those problems that combine learning, statistical learning, and decision-making when there is a lot of uncertainty in the environment. And the problem has two important characteristics. The first one is banded feedback. That is, when customer little t arrive, we observe xt, the feature of the customer, and then we make a decision at. I know the reward only associated with that decision. I don't know the reward for other decisions. Does this make sense? That's why I say this is banded feedback. I know the reward for the decision I choose. I have no idea how much I would have collected if I chose another decision. That's one challenge. The second challenge is heterogeneity. The effectiveness of an action, of a decision, obviously depends on the context, but the context space is huge. There is no way to explore all of it. So how can I learn across context? That is an important challenge because I don't know which context will arrive tomorrow. And so I need something that learn across context, and I need something that try to predict the impact of a specific action. The literature on this problem is very, very rich. It brings together research in operation research, computer science, statistics, and economics, and it's vast research. I'm highlighting here just a few examples of algorithms that recently were published. One of the reasons this is a very active research area of research is because there are many, many different applications for the contextual bandit problem, from recommendation system to ride-hailing platform to dynamic pricing. This is a paper that I did with my PhD student, Chris Ferrer-Johnson, who is at Harvard, and He Wang, who is at Georgia Tech. Healthcare application. So the number of applications is huge. Just to illustrate why this is so relevant to operations, here are two examples. Yesterday, to prepare for this talk, I logged on Amazon platform, and the platform immediately gave me a recommendation. Basically, the application is you have K product, customers arrive one after another. When a customer arrives, you observe the feature vector of the customer, you then recommend a product, and the reward is generated based on some unknown function F star. Personalized medicine is now a hot area in healthcare. In this case, you may have K different treatments. A treatment perhaps is at dose level. Patient arrives sequentially to the platform. We observe the feature of the individual patient. We then subscribe a treatment, and the objective is to learn about the efficacy of the different treatment. So the efficacy is generated by some unknown function F star. And so the application are, of course, coming from electronic commerce to healthcare, even, of course, to supply chain. So let's pinpoint the challenge. We are interested in the contextual bandit when the class of function F is general. I will denote it by big F. We will assume that the ground truth F star belong to this class, and I give you a few examples earlier. Now, when you think about the contextual bandit, there are two challenges. The first is statistical. You give me a class of function big F, I want to show you that I can find the optimal regret. You change it to another class of function, I want to show you that even for the new one, I find the optimal regret. So independent of which class of function you show me, I want to make sure that I'm able to generate the optimal regret. The second is a computational challenge. We want to make sure that the algorithm is computationally efficient. I will define precisely what I mean by computationally efficient algorithm in a few slides, but the intuition when I say computationally efficient algorithm is clear. If you look at existing algorithms, they are either statistically optimal or computationally efficient, but not both. For example, if you look at popular algorithms like Thompson sampling and UCB, these are computationally efficient algorithms, but they are guaranteed to find the optimal regret only for special classes of function, like parametric, like linear, and so forth and so on. On the other hand, exponential weighting or elimination-based methods guarantee to find the optimal regret, but they are computationally intractable. So we are looking for something that closes the gap on both challenges. So what is specifically the research question, and how do I define computationally efficient? So suppose you are given a general class of function f. We know that in offline, given IID data, we know how to generate a predictor f hat such that this predictor achieves a low estimation error, and it can be computed efficiently. This we know how to do very well in the offline space. Questions that we ask, is it possible to take the online version of the problem and reduce it to the offline, and therefore benefit from all the recent development in the offline space? More precisely, suppose we are given a class F and an offline regression oracle, for example, least square regression oracle, or ridge, or lasso. Here is my question. Can I design an algorithm for the contextual bandit such that this algorithm will achieve the optimal regret whenever the offline regression oracle achieve the optimal estimation error, the minimum estimation error? Does this make sense? So notice the two problems, the offline and the online, have different objectives. One is regret, one is estimation error. What I want to do is to make sure that whenever the offline achieves the minimum estimation error, the optimal estimation error, the online will achieve the optimal regret. And I want to do it in a way that it requires no more computation than just calling the offline regression oracle. This problem, precisely the way I describe it, has been mentioned over and over again in the CS literature as an important open problem. This is the problem that we are focusing on in this research. Now, you may wonder not why it's important. Why it's important, I explain, and if you have some experience in statistical learning, you understand why it's important. But why is it challenging? There are, in fact, two important challenges that I need to describe. One associated with confidence bound and the other one associated with dependent action. Let me explain each one of them. If you think about classical algorithms like UCB and Thompson sampling, they work only for certain parametric models because they require the ability to calculate, to build confidence bound for every pair of context and decision. We know from statistics that you can do it only for special classes of the function f. You cannot do this for general classes. And it's because of this that Foster and his co-author in 2018 proposed a computationally efficient confidence-bound based algorithm, basically doing what we want to do, but using the ability to build confidence-bound and offline regression. The problem here is that it works, as I explained, only for certain function classes. It doesn't work in general because we cannot develop effective confidence bound for every pair of context and decisions when the class of function is general. So that's one problem. The second problem is very intuitive. The offline algorithm assumes that data is IID. But in online, the data is nothing by IID. My decision today depends on what I observed yesterday. So the IID assumption is completely violated. So how can I reduce a problem whose data is not IID into an environment that requires IID data? It's exactly because of this reason that my colleagues from MIT, Dylan Foster and Sasha Ratlin, propose an optimal and efficient algorithm for the same problem that we are focusing on by assuming access to online regression oracle. The beauty of online regression oracle, it does not require IID, so that's great. The problem with online regression oracle is that we have effective algorithms only for special classes of function. So we are moving in the right direction, but you can see that we are hitting a wall every time we are trying to generalize the algorithm to any class of function bigger. So here is our contribution. We developed the first optimal and efficient black box reduction from the general online, general contextual balance to the offline model. Our algorithm builds on ideas that have been published in the CS literature. We are using ideas from an old paper by Abe and Long that suggested, and I highlight what was the suggestion by Abe and Long, Agrawell 2014, and the paper I mentioned just in the previous slide, Dylan Foster and Sasha Ratlin. But our analysis is completely different than the analysis in this paper. We are basically using duality, if you will, to show that the reduction is possible. But the bottom line insight from our analysis that any advance in offline regression can be immediately transferred into advances in the online contextual bandit, both advancement on statistical aspect and advancement on computational aspect. Just to highlight, before I dive into our algorithm and the main theory, just to highlight the contribution in our research. If you look at multiple algorithms, for example, regression, regressor elimination algorithm that was developed in 2012, it guaranteed to find the optimal regret for any function class, but it's completely intractable. 2 years later, Agrawal and his co-author came up with a new algorithm that again guaranteed to find the optimal regret, and then by making a polynomial, if you will, number of calls to an offline classification oracle. The problem is this: every time you make this call, you need to solve an NP-hard problem. So that's not computationally efficient. RegCB, this is the algorithm by Foster and his co-author in 2018, actually is going in the direction that we will go. Make polynomial number of calls to an offline regression oracle. That's great, but it only guarantees optimal regret in special cases. In general, it's suboptimal. SquareCB, this is the one by Dylan Foster and Sasha Racklin, finds the optimal regret by making polynomial number of call to an online regression oracle. That's all great. The only problem is it can do it only when you have an available algorithm for online regression oracle, but we don't have algorithms for many classes of functions. Falcon, our algorithm, guaranteed to find the optimal regret by making, look at this, log T calls to the offline regression oracles that you are using when T is unknown in advance, and log T if T is known in advance. So in terms of computational complexity, our algorithm is equivalent to that of solving a few offline regression problems. So where is the name monster come from? Remember, we call our paper bypassing the monster. In the contextual bandit literature, monster refer to algorithms that require a huge amount of computation. The first paper to refer to their analysis and their paper, the first people to refer to their paper as a monster paper is Dudik and his co-authors. They develop an algorithm that finds the optimal regret, but it requires, this is a statement from their analysis, a monster amount of computation. As I mentioned, 2014, Agrawal and his co-authors were able to reduce the number of computations, but it requires solving a sequence of NP-hard problems. That's why they call their paper Taming the Monster. And we show that you can bypass the monster just by focusing on this assumption that the ground truth belong to as a class of function. So what is this algorithm that I am referring to that allow us to achieve this objective? The algorithm, as you will see, is very simple. We have three components in the algorithm. One is an epoch schedule. We take the time horizon and we divide it into sub-interval using an epoch schedule. At the beginning of each sub-interval, I'm going to make a single call to the offline regression oracle and use whatever I got from the offline regression oracle, but I'm not going to use it in a naive way, in a greedy way, because I'm not sure that the predictive function that I got from the offline regression oracle is the correct one. And so I will use a randomized algorithm. This idea of randomized algorithm was initially suggested by Abe and Long for a class of linear functions, and later on was used by Foster and Racklin in their recent paper. We are using it in a different way, but it's the same ideas that come from Abe and Long. We call our algorithm Falcon for fast least square regression oracle because for obvious reasons. So let me give you now detail on the three components of the algorithm. We take the time horizon and we split it using an epoch schedule. You notice just by inspection that as we move across time, the length of the sub-interval is increasing. When we don't know how many customers will arrive, we use a geometric sequence. This implies that the number of sub-interval is log of t. If we know how many customers arrive, like in healthcare, when we run an experimentation, we know how many people we will log into the platform, then we can reduce the computational complexity to log t, calls to the regression oracle. Now, once we made a call to the regression oracle at the beginning of an epoch, we have a predictive function, f, but we are not sure that this correctly represents the ground truth. That's where I'm going to use a randomized algorithm to explore and exploit. And the idea is that at the beginning of a subinterval or epoch m, I'm going to use least square, or if you prefer other oracles like Ridge or Lasso, we use this to generate a predictor f. As I mentioned, we are not going to use it in a naive way. We are going to use a randomized algorithm. Here is the way the randomized algorithm works. So we are now at the beginning of epoch m. I'm going to define a learning rate gamma. You notice that just by definition, as I move from epoch to epoch, the learning rate is going to increase. Then at time little t, a customer arrives, right? Remember, at the beginning of the epoch, I generated, using our offline oracle, a predictive function f. Customer little t arrive, I observe the context of this customer, and then I need to make a decision. I will call a hat the greedy action, the one that is best if f hat was correct. I don't know that f hat is correct, but if it was, this is the best decision. Now, I'm not necessarily going to use the greedy action. I am going to flip a coin to decide what to do according to this probability. That is to say, I will choose an action A, not the greedy action, with probability inversely proportional, as you can see here, to the gap between the value of the predictive function under the greedy action and the value of the predictive function under action A. The bigger the gap, the smaller the probability. And with the remaining probabilities, I'm going to choose the greedy action. So you can see that these two actions, greedy action or non-greedy action, is really playing on the trade-off between exploration, when I choose a non-greedy action, and exploitation. Notice something important. The probabilities of choosing, for example, the non-greedy action, highly dependent on the learning rate. And you see what's happening. As I move from epoch to epoch, the learning rate increases because I learn more. That's the intuition. Since I learn more, I'm going to use the probability of not choosing the greedy action. Does this make sense? I learn more. I want to use less frequently the non-greedy and more frequently the greedy. That's how the learning rate plays a role in our algorithm. So what can we prove for this simple algorithm? The first thing is, when you have a finite function class, we show that Falcon guarantee an expected regret of no more than square root of k. Remember, k is the number of action, number of decisions, times t, time log of f, using log t calls to the least square regression oracle when t is unknown, or reducing it if t is known. The beauty of this result is that there is a matching lower bound, implies that our algorithm finds the optimal regret for finite function class. Now you may say finite function class is one example. What about general? Here is the result for general. To explain the result for general, let's start from the offline learning. Given NIID samples and an offline oracle, that generate a predictor f hat. Let's look at the expected square error. And I will call ER to be a bound, right, on the error, or ER is the estimation error guarantee. And obviously, the estimation error guarantee depends on how many data points I have and what is the function class F. We prove the following, that given an offline regression oracle whose estimation error guarantees ER, Falcon provide a guarantee of regret of no more than square root of k ER times t, again using log t calls when t is unknown, or log t if t is known. The beauty of this is there is a matching lower bound, implying that our algorithm finds the optimal regret whenever ER is the minimum error. Exactly the requirement that I defined at the beginning of the research. Whenever the offline finds the minimum error, our algorithm finds the optimal regret. So this has immediate implication. For example, if the function class is linear with dimension d, we know that least square guaranteed estimation error proportional to d over n. Immediately we get a new result on the optimal regret in this case, which is proportional to square root kt d plus log t. If there is, it's the class of function f is linear with sparsity s, then we know that lasso ensure an ER no more than s, the sparsity log d divided by n. We show immediately that Falcon guarantee a regret of square root of ks t times log d. And there are, you can look at the paper, lots of examples where we provide new results on the optimal regret. This is all very nice, but you may be asking, this come from theory, how effective this algorithm is in practice. Let me show you. So we tested the performance of our algorithm on 3 real-world data sets: multi-class classification, recommendation problem, and price optimization models. We took 10 multi-class classification data sets, 2 recommendation data sets. We took them from open sources. Everyone that has an algorithm in this space applies their algorithm to test the performance. Let me explain the classification problem. Classification problems are really fundamental problem in machine learning. They are used for recognizing handwriting, face recognition, customer segmentation. You can see here examples that come from a variety of applications. The way error is measured, if the algorithm classify a customer correctly, then there is 0 error. When we make a mistake, the loss is 1, and you want to see what the accuracy. Recommendation is basically recommending a product for a customer. When a customer arrives, we want to recommend a product that she likes the most. If we recommend a product that is highly ranked, then we incur smaller loss. Otherwise, the loss is high. And this appears everywhere: Amazon, Netflix, Google, and so forth and so on. We compare the performance of our algorithm, right, Falcon, against 8 existing algorithms that we took from this VW open source library. Who are the algorithm? One is greedy, just use the greedy action. Epsilon greedy is similar in philosophy to our algorithm. With some probability, you choose a greedy action, and then with uniform probability, you use all the other actions. Then 2 versions of Taming the Monster algorithm, 2 versions of Thompson sampling. And then the best, until we did our research, was RegCB, the one by Foster and his co-author. They have 2 versions, elimination and optimistic. We tested against both. And you can see the result here. Let me explain what we can see here. Look just at the inside metrics here. There are the 8 algorithms that we are testing against. from greedy all the way to Rexy optimistic. And what we are doing here is what is classical in this literature. Look at the win-loss difference of row against column. So for example, let's take back greedy against greedy on the 12 data sets. Suppose that back greedy was significantly better on 6 problems. Greedy was significantly better on 2 problems, and the rest is statistically, the difference is statistically not significant. Then we record 6 minus 2 or 4. You notice that, like in the literature, Rexy elimination, Rexy optimistic are the best. We tested 3 versions of our algorithm because remember, our algorithm is very general. Version 1 is just assume linear function class and least square estimator. Falcon 2, assume linear class and ridge. And Falcon 3, just assume a regression tree, a general class, and use gradient boosting. And you can see we are in general doing well, but the best is Falcon 3, which assume general class of function. We then tested, and I will stop in 1 minute, then tested it in a dynamic pricing setting. We got data from Columbia University Center of Pricing and Revenue Management. The data include 200,000 transactions. Each transaction represents a customer with more than 100 different features. We reduce the total number of features to the 5 most important ones. I'm showing you them here. And then we use counterfactual to understand the probability of responding to different prices. We have 2 settings. In setting 1, we allow price range from $500 to $7,500, and we have 15 price choices. In the second setting, we have a price range between 1,000 to 10,000, and we have 10 different choices of prices. And again, I'm testing our algorithm against the 8 different algorithms that I mentioned earlier. If you look at this table, you can see average revenue generated by each one of the algorithm for setting 1 and for setting 2. Falcon dominates them. In this case, when I apply Falcon, we assume linear class of function and least square oracle. You can see on the figure at the bottom, I'm showing you cumulative revenue for setting 1 and for setting 2. Blue represent Falcon. The other colors are all the other algorithm. You can see that when you look at cumulative revenue, Falcon dominates. But the nice thing, if you know something about revenue management, is that revenue is not a linear function of price. So we said, okay, our algorithm can be flexible. Let's see. We tested our algorithm in 3 settings: linear function class and least square, linear function and ridge, and regression tree and gradient boosting algorithm. And you can see in the general, we dominate all the other algorithms significantly. Now, our paper, Anna, was posted on arXiv in March of 2020. Very quickly after our paper was posted, many extensions were written by others. The first extension is by us. Together with Dylan Foster and Sasha Racklin, we extended as a result from min-max regret to instant dependent regret, and also to reinforcement learning. Under, of course, some assumption on the reinforcement learning. Asaf Zvi and his PhD student from Columbia University extended the result to infinite action. Exactly what we did, but for infinite action. People from Stanford to model where an F is misspecified, people from USC to non-stationary contextual bandit, people from Amazon to combinatorial action space, people from Stanford to model selection, and so forth and so on. This is really one of the most remarkable observations that I've made, that in a span of 6 months, about 10 papers followed the research that I described to you in this talk. So thank you very much, Anna, for giving me the opportunity, and we can take some questions and comments from the audience.
Thank you, David. The hour really flew by. We only have a few minutes, but please, I leave it open to the audience for a couple of questions, and perhaps those interested can stay for a little longer and we can have a further discussion.
Or they can send a question on the chat and you can open the chat and just read the question.
I will check the chat, but I would really appreciate if you unmute yourselves and ask the question. It's more interactive, so please feel free to do so.
Anna, maybe one question from me. I was thinking, like, we saw some of the results. Professor Simchi-Levi, like, what are you thinking in terms of like the context that you have applications in? What improvement do you expect? Like all the applications that you've already worked with industry, what's the impact really then in practice?
Michael, so it's really a great question, which is what motivated this research. Remember when I talked about the data science lab, I said we did some work with airline and then we did some work with insurance. And every time we did the work, we needed to change the algorithm to make sure that it feeds the class of functions that you have in a specific environment. This was frustrating. Why in the offline space, I don't need to do that, but in the online space, I do need to do that. And so this was an answer to the question that indeed there is a general mechanism that allows you to have basically the same algorithm for generic class of function. That to me is the main impact. And the surprising thing about the algorithm is that it does better than customized algorithm. Look at this. If you just focus on these metrics and you look at Thompson sampling under linear, right? Thompson sampling is a great algorithm. And we use here two versions of Thompson, yet the algorithm I described here does very, very well. So it's really motivated by your question.
That makes sense. Thank you.
Any other comment or question? So I should point out, because this is a talk for a large audience, that this was done with my PhD student, Yin-John Xu, who is right now, Anna, you will be happy to know, in the market looking for an academic job.
I hope he has applied to our position. Thank you.
Yep. Very good.
I'm wondering, David, is there a good story behind the name Falcon?
Beautiful. Falcon is considered the fastest bird, the fastest animal on Earth. So that's why this picture is of Falcon, and if you search, it's considered fastest animal on Earth. This is why we find the right unit to make sure it's called Falcon.
Very nice.
Yeah.
I would like to ask everyone to put their videos on. We're just going to take a quick picture of the attendees to have a memory of this event. So for those of you who are willing and able to turn your cameras on, we'll just take a quick picture of the audience. So David, if you could just stop sharing the screen so that we can see everybody, and it's just a memory of the event.
You will record, you will take a picture?
Mm-hmm.
Beautiful.
All right, done. Thank you.
One comment, Dr. Simchi-Levi, about I was thinking for more extension, maybe it's useful to use kriging and co-kriging algorithm. So for the regression part, So for different application.
I agree. And from a theory point of view, you want to ask, does it help reduce or find the minimum estimation error, right? From practical point of view, we need to test the impact, but I suspect that you are right.
Yeah. Thank you.
Thank you.
All right, thank you very much, everyone. We are gonna close now. Thank you so much, David. This was wonderful.
Thank you.
Thank you so much.
Thank you.